Okay, so thanks for inviting me along today. I'm going to give a very wide-ranging talk today about black holes and dark energy, a cosmic history. It is a very, as I said, it's a very wide-ranging subject. It's based on two papers that were published earlier this year, and we have a group of astronomers led by the astronomers at University of Hawai'i, and really trying to link together some of these cosmic mysteries that generate so much interest for black holes and also dark energy. So this talk is basically on three areas. I put on three sides of a triangle: dark energy, black holes, and galaxy evolution. Now, people will spend their entire careers on one side of this triangle, and it's probably accurate to say that on that author list of the papers, there's probably no single author who understands every single part of all the work that we've been doing. But I'll try my best to lead everyone through it today. So I'm going to start off with a little bit of a background and introduction, looking at an accelerating universe. And our universe, we all know, started in a Big Bang, something like 13.7 billion years ago, and has been expanding ever since, with the galaxies and the stars we see today all moving away from each other. So this is all about gravity. When we think about gravity, the classical thing is the apple that fell on Newton's head. And here we've got a little cartoon depiction of that apple. Whether it happened or not, I believe that tree is actually still there. But what have apples got to do with the fate of the universe? So on the right panel, we've got two people throwing apples up in the air. Now, the guy on the left, he throws the apple up pretty weakly. It goes up to some height, and then gravity pulls it back down to Earth again. Whereas the girl on the right, she gives it a really good, really good throw, and the apple escapes the Earth's gravity and continues off into space. And that's very much like the possible fate of our universe. So looking at instead how our universe behaves. So on the vertical axis, I've got the size of the universe, and on the horizontal, we've got time. So we could live in one of many different universes. It's probably safe to say we don't live in the yellow line, the empty universe. However, it's possible that we live on a green line. This is where the girl throws the apple up, and it goes so fast that it escapes gravity, basically continues forever. So the universe expands forever. The pink line at the bottom is more like the boy throwing the apple up. He doesn't give it a big enough throw, so the universe expands to some maximum size, and then the gravity within the universe will conspire to pull everything back together again and end in a big crunch. And there's also this blue line, this kind of boundary case, where we just give the apple enough push that it escapes the gravity at time infinity. So it's like a limiting case. So which universe do we live in? So this is a picture of a baby universe. It's taken 300,000 years after the Big Bang. So it's the earliest picture of the universe that you can really get. It's taken by the Planck satellite. And what it tells us is, when we analyze the data, is that we live in a flat universe. So that means, for example, if we could draw a massive triangle in space and we add up the angles, we'd find out the angles added up to 180 degrees. So it's Euclidean geometry, as you would say. Whereas if we lived in different universes, like a universe that expands to some maximum, then goes back to zero again, if we did the angle measurements in that universe, we'd find out the angles on the triangle would add up to more than 180 degrees. So the geometry universe is measurable. We can find out the sort of universe we live in. But anyway, we live in a flat universe, which means there's enough stuff in the universe to flatten it. So we have enough matter, enough mass, enough energy to flatten our universe. So unfortunately, that's only the beginning of the story. Dark matter is probably familiar to everyone, at least in the name. So when we add up all the atoms that are created in the Big Bang, we find out it only gives us about 5% of the density required to flatten the universe. So there's not enough stuff in the universe, basically, to make it flat. When we observe how fast galaxies are moving, or how fast stars are moving around the centers of galaxies, for example, we find out that the atoms that we see, the light matter, the luminous matter, is not enough to explain the movement of galaxies and stars in the universe. In fact, it's about only 1/6 of what we actually observe. So we know that about 80-odd% of the universe is containing matter that's dark. We can't see it. So we've got normal matter, what we see, all the stuff that makes up the periodic table, and then we know we've got some dark matter already. So we've already got some problems and mysteries, and we can think of this like an iceberg, where we see the tip of the iceberg. That's all the atoms in the universe. That's all your carbon, your oxygen, all the stuff that makes up everything we see. But below the surface, you've got the rest of the iceberg, and that's the dark matter, the stuff you can't see. So this is the universe which we thought we lived in until about 1998. In 1998, the Hubble Space Telescope looked at a bunch of supernovae. So supernovae are exploding stars, what happens to massive stars at the end of their life. So they're gigantic explosions that leave behind these lovely nebula, these gas clouds, for example, like the Crab Nebula we see in space. So what astronomers found, in fact, is when they looked at these supernovae, the supernovae were fainter than what was expected, which meant that the universe must have increased in size a lot faster than what was originally assumed. Now, the only way that could happen was, in fact, the universe was not actually expanding and slowly being slowed down by gravity. In fact, it was accelerating, which was something completely new. And this work actually won the Nobel Prize for Physics in 2011. So we've got now our universe, started in the Big Bang 13.7 billion years ago. It starts expanding. Dark matter and the stuff in the universe and the power of gravity tries to slow that expansion down. But 4 billion years ago, something strange happened and the universe started expanding. So what was driving the expansion in the universe? We gave this phenomenon the term dark energy. So dark energy is something that accelerates the universe. So now we've got three components that make up our universe. And we can think now, go back to our iceberg analogy. The stuff above the water, what we can see are the normal atoms. So like I said, this is the stuff that makes up the periodic table. Below the surface, you've got the dark matter, and that comprises about 27% of the stuff that we need to flatten the universe. But by far, the vast majority of stuff in the universe is this dark energy. And you can imagine this dark energy being the ocean that the iceberg is floating in. So I should say, when we talk about how much we understand about the universe, all we understand really is that 5%, the bit above the surface of the water. We know dark matter's there, we know dark energy is there, but we have no real idea or no concrete idea about what this stuff is. So it just shows how little we still understand about the universe. So what is this dark energy? What could it be? So I'm not going to show many equations here, and we don't have to understand the individual terms in these equations. But this is the Einstein equation. So Einstein's famous equation of general relativity, and it can be split into the yellow part, which is all about geometry, and the green part, which is all about mass and energy. And there's this famous connection between mass and geometry in the universe, where the matter in the universe tells space and time how to curve, and space-time tells matter how to move. And we can see that in this little cartoon here, where we have the sun at the center, and you can imagine the sun being on space-time. We call it, it's like a rubber sheet. The sun is heavy enough to make an indentation in this space and time, this rubber sheet. And the Earth, therefore, goes around the sun, not because of the force of gravity, but in fact, because it's going around this depression in space and time that the sun is causing. So general relativity is, you can think of it as a geometrical theory, which is fundamentally different from the other forces that we see in nature. Now, the thing is, this equation, this Einstein equation, doesn't give a static solution for the universe. So the universe must either be expanding or contracting, but it can't be standing still. Problem was, when Einstein postulated his theories, the fashion or the vogue was very, very much for a static universe. So Einstein had a bit of a panic, and like all good physicists, he put a fudge factor into his equation to save the day. to basically to stop the universe from either expanding or contracting. And he put this fudge factor in this cosmological constant term into his equation. And basically, this balanced the equation so it was neither expanding or contracting. And he later went on to say it was the biggest mistake of his life. We now know that we've got this dark energy, and the dark energy actually acts very, very much like a cosmological constant. So we're going back, we're turning back time 100 years or so, and we're going back saying, maybe this is right. Maybe we do have a cosmological constant in these equations. But what is this dark energy? We know that our history of the universe, we accelerated at an early stage called inflation, and then we had this regular expansion that we spoke about. And then we had the dark energy kicking in about 4 billion years ago. So we know the universe goes through various stages of expansion. Now, the first person really to give some idea about what this dark energy might be was O.S. Kleiner in 1966 in quite an obscure paper that was published. And he postulated that this dark energy was something that we now term as vacuum energy, the energy of the vacuum of space itself. So space isn't really empty. Even the vacuum of space is really a seething, bubbling mass of particles popping in and out of existence. It's a little bit like a cosmological Casimir effect when you put two metal plates together. So this vacuum energy would be responsible for a very early inflationary phase of the universe, and it would also be responsible for the current observed acceleration of the universe. And it can also provide an endpoint for gravitational collapse, which again kind of leads us on to the next part of this this talk here, which is towards black holes, because we're looking at endpoints of gravitational collapse for this dark energy. So is it possible it's black holes? So if I pause there at the end of part one. So I don't know if you've got any questions at this point. Well, maybe we can take one or two or something, because we need to obviously cover everything today. If we don't have anything, I'll just
no. I've asked if just to let everybody know, we've kind of cunningly cut this, or Chris has cunningly chopped it up into 4 parts. So. Yeah, we'll have a quick pause. So there's a question from Max in the chat.
Yeah.
Chris, what tells us that dark energy came into effect 4 billion years ago?
Sure. Yeah, so we can look at, for example, distant supernova at different distances, and we can go back from local to intermediate to high distances in the universe, and we can model how their brightness changes as a function of time and distance away from us. So we can see that this supernova effect really kicks in about 4 billion years ago, which sets that mark roughly where the dark energy kicks in.
Okay, thanks for that. If there's no other questions, Chris, suggest you crack on.
Let's crack on then. Okay, so let's move to part 2, which is black holes. So we're still kind of like really on the background here. So black holes, let's have a brief history of black holes here. So they've actually been theorized for over 200 years. There's a paper going back to 1873, John Mitchell, where he referred to these things called dark stars, where the gravity would be so powerful that these little light particles wouldn't be able to escape them. The actual term black hole was coined in the 1960s by John Wheeler. So black holes are basically the end point of massive stars. The massive stars blow up, their cores collapse, and these cores collapse in a runaway effect. They keep on collapsing and collapsing and collapsing. The strength of gravity increases until what we're left with at the end is this really this unstoppable runaway effect, where we're using this rubber sheet analogy again. So imagine if you had something so heavy that the rubber sheet, this indentation in the rubber sheet, just went down and down and down and never stopped going down. That's basically what a classical black hole is. Now, we define a point where light can't escape a black hole because the gravity is so strong. Now, we call that point roughly the the event horizon, which is, it's a common term. We see it in a lot of science fiction things, right? But the event horizon is basically the point of no return, where the strength of gravity is so great that it matches the speed of light. The escape velocity is basically the speed of light. So crossing the event horizon is the point of no return. You cross the event horizon in a black hole, and you're done for. There's no escape. Traveling down the throat of that black hole, we reach the singularity at the center. This is where the maths and the physics break down. You get infinite mass, infinite density, and zero volume, infinite temperature. It's actually the end of time. In fact, if you look at these black holes, so you're traveling towards the end of time inside a black hole. You'll be crushed into oblivion, or so conventional theory goes. So that's basically our classical theory of what a black hole looks like. So as I said, black holes are formed. They can form when massive stars explode and they end their lives. This is a stellar life cycle picture here. On the top of the stellar life cycle, we've got a small star like our sun. So our sun will, after another 5 billion years or so, will expand to be a red giant. Then it will blow off its outer layers and form one of these nice, beautiful planetary nebula. And then all that's left is this cinder of what used to be a white dwarf. It's a white dwarf, and a white dwarf is an object. It's about the size of the Earth, with a large fraction of the sun's mass locked inside it. So an extremely dense object. However, bigger stars, they party hard and live shorter lives. So stars more than about eight times the mass of the sun or so, they'll expand to be a red supergiant. They'll undergo catastrophic collapse as they lose the battle against gravity. This will cause the core to implode and send shockwaves out in what we call a supernova that we heard about earlier. Now, depending on the initial size of that star, you're going to get a neutron star, which is the mass of the star packed into the size of a small city, or you're going to get black hole, where the gravity is so strong that it's continuing to crush the core of that star into oblivion. So that's one way black holes can be formed. It's not the only. It's not necessarily the only way. Black holes come in two flavors. We have stellar mass black holes. This is sort of like the endpoints of stars. We also have what we call supermassive black holes. Now, supermassive black holes are formed at the center of galaxies. So initially, they're formed by extremely large stars, or stars falling onto large black holes, or even black holes merging together. Every galaxy probably has a supermassive black hole at the center, or at least the vast majority. Our galaxy, the Milky Way, also has a black hole at the center. It's Sagittarius A star. And in fact, now, over the last few years, we've actually had the first actual images of black holes. So for the first time, we've actually got here, these are actually pictures of actual black holes. So these were taken with the Event Horizon telescope. So we've got the one on the left here is a supermassive black hole at the center of a distant galaxy, M87, about 55 million light years away. Now, this black hole is something like 6 billion suns in terms of its mass. So it's absolutely colossal. The one on the right hand side, Sagittarius A star, this is the black hole at the center of the Milky Way. So it's instead of being 55 million light years away, it's a paltry 27,000 LIGO instrument. So the LIGO instrument was where you had these two long L-shaped detector systems that can measure gravitational waves that are ripples in space and time itself. You see gravitational waves, for example, when two black holes collide and merge together. Now, some of the LIGO results also pointed to some strange things with black holes. For example, some of the black hole mergers they see are made with highly unequal mass components, which is quite difficult to reconcile with the current formation scenarios. So we have lots of little clues really about that we're not quite understanding black holes.
What determines a supernova becoming a black hole or a neutron star?
Yeah, so the basic thing that depends on it is how big the original star was. So you've got something like maybe that's bigger than eight solar masses is going to become a black hole, and something smaller than that is going to become a neutron star. It's not the only way. It's not the only way a black hole can form. You can also form a black hole by stuff piling onto a white dwarf or piling onto a neutron star, for example. But basically, it's how big the initial star is.
Could I ask a quick question? It's an easy question. I don't know if it's a complex answer. We hear about things like Hawking radiation. So whereas what you said so far is everything gets gobbled up.
So Hawking radiation we may come back to that. Hawking radiation is it's a mechanism theorized by obviously Stephen Hawking, where black holes can actually emit radiation. Now, if you're emitting radiation, then the energy of the black hole must be decreasing. So it's a way, in theory, that black holes can actually evaporate over time. So black holes, in theory, could evaporate and end in a burst of energy. One of the issues with Hawking radiation here is that the actual evaporation time for Hawking radiation is absolutely immense. I mean, there's no way that this can be measured on time scales, even of necessarily billions of years. So it's a theoretical mechanism, but it's very, very hard to sort of get observational evidence for this.
Okay, thanks. We've got two questions in the chat. Yeah, how did you take a photograph of the black hole if light can't escape one?
Yeah, so basically this Event Horizon telescope is not really one telescope. It's made up of many telescopes. So it's made up, for example, of ALMA, which is a large dish array in Chile. And also there's the IRAM 30-meter telescope, the James Clerk Maxwell telescope on Hawaii, the large millimeter telescope again in South America, lots of telescopes, including the South Pole telescope and the Greenland telescope as well. And basically, it's made up in the same way we kind of make radio images, where you're taking lots of detections with lots of telescopes and then combining those together to make an image of the black hole. Okay, we've got two more questions, but Chris, do you think we should push on at this point? Yeah, I can push on. There's the first question about the event horizons. Does it affect your theory? Yes, it does very much, and we'll come back to that. And what would a black hole evaporate into? It would explode in a burst of high intensity radiation. Okay, so let's kick on to part 3. So how do black holes grow? We know they need to grow because we see, for example, these black holes within quasars are extremely large. We see black hole mergers can have black holes of disproportionate sizes. So let's look at some of the mechanisms by which black holes grow. Now, we know black holes grow with time. In fact, we know they're very, very closely linked to star formation, so how stars are forming in galaxies as well. And in fact, what we've got here on this graph here, we've got the orange points, which are measurements of how fast stars are forming. And we've got this gray curve, which is a measurement of how fast matter is accreting or falling onto black holes. Now, the bottom axis is redshift, which is basically measuring distance in the universe, or indeed counting back in time towards the Big Bang. So redshift of 0 is now, redshift of 10 is in the past. But what we see is the star formation kind of peaks at this redshift between 1 and 2. So it goes up and then it starts to decline. And we also see the same thing happens to the black hole accretion as well. So we think that black holes and star formation are inextricably linked together. In fact, the total black hole mass in the local universe must arise from processes, that have assembled black hole masses across the history of the universe. So we know that stars and black holes are linked together. In fact, we also see a correlation between the mass of galaxies, or rather the mass of the central part of the galaxy, the bulge in the middle of the galaxy. So the bulge mass and the black hole mass. And again, we see it's in an ideal universe, it would be a straight line. So we see black hole mass up the vertical axis, and we see the mass of the central bulge, which is basically the mass of stars here, along the x-axis, and we see a nice straight line. Reality is a little bit is a little bit more complex. So in reality, this is the same. This is now the same plot. So you've got black hole mass and effectively stellar mass here, and all the dots are different observations of different types of galaxies at different redshifts, and then the lines of various models that that people have made. So it's not an exact, one-on-one correlation. It's not a completely diagonal straight line. However, if we look at the many computer simulations that are made, so not shown on this plot, there's been lots of computer simulations that are made. All these simulations basically agree that this black hole mass and the stellar mass is correlated. They're linked together. Okay, so we'd like to measure this. We'd like to see how the star mass and the black hole mass changes as a function of time, see if we can get insight on how fast black holes are growing. So we need to select a good sample of galaxies that we can measure black hole masses in here. And this is quite difficult to do. We can look at different types of galaxies. And what we've got here now are, we've got two examples. So we've got ellipticals and we've got spirals. So spiral galaxies are like the Milky Way, galaxy that we live in, or our nearby neighbor Andromeda. And spiral galaxies have, lots of star formation. There's lots of dust and gas in these galaxies. That's what makes up the spiral arms. And spirals are quite messy, and it's quite difficult to get a proper measure of a black hole mass inside a spiral galaxy because there's so much going on in terms of the star formation and dust and gas falling into the black holes, etc., etc. On the other hand, we've got ellipticals. Now, ellipticals are very sort of amorphously shaped galaxies. They don't have the beautiful spiral arm structure. They're generally older than spiral galaxies. They've used a lot of their dust and gas. They've finished their star formation. So elliptical galaxies are quite cool if you want to study black holes because they're much simpler. And we know that if we see black hole growth in ellipticals, it's not going to be due to sort of like, swallowing up other stars or star formation in that galaxy, because the star formation is minimal in that galaxy. So we're going to choose ellipticals, and we're going to look at 3 different families of ellipticals divided by distance. So we're going to take a sample of local galaxies, local ellipticals at redshift 0. And these are massive quiescent elliptical galaxies that are all very, very, very well studied. Then we're going to take an intermediate sample, and we're going to look at ellipticals at about redshift of 0.8. And these are taken from a satellite called WISE. So this was WISE surveyed the whole sky at infrared wavelengths. So we've got a lot to choose from here. And then we've got we're going to push out to greater distances. Now, the farther we push out, the more difficult it becomes, because galaxies, becoming, smaller. We need big telescopes with very strong resolution, very high resolution to look at the detail of these galaxies. So we push out to redshift 1.6, and we're using the Cosmos survey, which was an area which was observed by the Hubble Space Telescope. So the best of what we could do at the present time here. So we've got these 3 samples of galaxies, and we're going to measure the mass in the stars, and we're going to measure the mass of the black holes in these galaxies, and we're going to try and recreate this this nice plot, or see if we can get how close we can get to this straight line here. Okay, so let's move on to the plot here. So this again, now we've got the mass of the black hole as measured at the y-axis, and we've got the mass of the stars measured along the x-axis. This is for our high redshift sample. So we should say here that, we haven't got thousands and thousands of galaxies in this sample, and we'll come back to that in terms of the caveats at the end, right? We're doing the best we can with what we've got available at the moment. Okay, but here is our high redshift sample on the black hole mass and the star mass axes. If we then add the intermediate sample from WISE, these are the blue markers here. And again, we have kind of like this this straight line. There is an offset in the line here. And then we have the local ellipticals. And again, now what we see here now is the local ellipticals are clearly lying higher in the black hole mass and star mass plane. What we'd expect is that all these would lie on the same area, right? Because we're assuming that these ellipticals are the same locally, intermediate, and at high redshift, which is a reasonable assumption with studies made. So we have to ask ourselves now, is this offset or what's the reason for this offset? We see an offset from the high to the intermediate to the local galaxies. So what is causing this offset, and how can we correct it? Because we know, astronomy is complicated. Astronomy is messy. We know there's corrections that we have to make in these samples. And in fact, we can calculate the shifts in both the stellar masses and the shifts in the black holes, and we can make these nice little plots here, where in an ideal world we would expect these three curves to overlap with each other, but instead we have the local galaxies in green, we have the intermediate sample in blue, and then we have the high redshift sample in red, and we see that they're not really overlapping at all here. Similar for the black holes, they're not overlapping. They're actually better than the stellar mass, which is interesting because we'll come back to that as well. But we see a black hole offset as well. So the stellar mass is off by about they're off by about 0.2 orders of magnitude. The black hole masses are actually the shifts are actually higher than that. So how do we explain this? So as I said, astronomy is messy. So we know there's stuff that we haven't taken into account. So this work, a lot of this work actually was trying to account for all the biases and all the uncertainties in the data. In fact, we created a dedicated bias pipeline, simulations trying to account for every single bias, every single uncertainty that we could think of. Or a different way of doing it is putting in slightly different input parameters to our assumptions and seeing how much that changes the output results. So we can look at biases, for example, like have we got the mass function, so the number of stars as a function of mass, is that correct? Is our mass to light ratio correct? Looking at virial measurements in distant galaxies, for example, how accurate are our measurements for the black hole mass in our high redshift galaxies? How accurate are our stellar dynamical measurements? Or, for example, have we accounted for residual accretion, stuff falling onto black holes that we haven't accounted for? The other sources of bias or uncertainties are these populations really ancestral? So can we say that local ellipticals are the same as intermediate, are the same as high redshift samples? Is the scaling relation, that black hole mass to stellar mass, is that wrong? I mean, we're assuming that the scaling relation doesn't evolve with time. Maybe it does. Different gas accretion scenarios, the way black holes grow from gas accretion. Again, this is difficult because we've chosen elliptical galaxies on purpose to minimize this. Dry mergers. So a dry merger is when two galaxies or two objects merge without dust and gas being involved. And also, for example, stellar mass loss. Can stars be stripped from galaxies by some mechanism which would reduce the stellar mass here? So we're taking all these different things into account. And in fact, one of the authors on the paper is specifically chosen because he's an expert in this field. So we have our bias and uncertainty pipeline, and we put all these effects into it, and we get a really interesting result out. So accounting for bias here, on the top we've got this uncertainties in the black hole masses, and on the bottom we've got the uncertainties in the star, the mass due to stars. Now when we correct for all the biases, we find the stars actually come together. These are the different samples. They come together rather well. So we can see that the bias corrections we've made do actually reconcile the mass in stars between the different samples. However, the black hole offsets become worse. And in fact, we now see, I mean, again, ideally we'd like these three curves to sit on top of each other, but instead we've got these three curves that are clearly distinct. The low redshift one, the intermediate distant one, and the distant sample are clearly separated. And these distances, or rather these uncertainties, are big. I mean, they're really big here. You've got 1.3 orders of magnitude here difference between the orange and the green lines. So something strange is going on here. So first of all, correcting for bias, correcting for uncertainties, the required stellar mass shifts are consistent with 0. So that's good news. However, the black holes we find are about 8 to 20 times more massive today than what they were 9 billion years ago between our local and our high redshift samples. So how can we explain this? So what we want to do, we need some physics to either shift the orange and the blue lines either to the left or up, for example, so they overlay with the local sample of galaxies. And there's various mechanisms that can do this. The problem is there's no mechanism or no one mechanism that can do this to the amount that we require. For example, if we look at stellar mass loss, we could perhaps explain away 20% of the stellar mass loss. We require something like 700% to actually sort of match these samples. And we also know that anything that grows a black hole, or any astrophysical process that grows a black hole, will also grow stars. For example, if you're pumping dust and gas onto a black hole to make them bigger, you're also going to have a corresponding increase in the star formation rate. So it's very difficult to find a mechanism that will account for the black hole mass difference without also affecting adversely our stellar mass measurements as well. Okay, so what's the solution? Could it be that multiple mechanisms are conspiring to work together? That might be possible, although growing just black holes preferentially without stars is really difficult. Poorly understood biases, yep, maybe. We don't understand a lot of things about it. But again, these differences, the actual differences in the masses we see are big. It's difficult to reconcile things with biases and uncertainties that we haven't taken into account. Or the other solution is that perhaps black holes grow in a way that's not related to astrophysical processes like accretion or mergers. So I'm going to, I'll stop there because that's the end of part 3 there. And I will look at...
there's a couple of questions. Yeah. So I'll read it out for everybody else. So why is it a reasonable assumption to say that masses of SMBH are the same? Seeing them as they are today, they would be more massive due to many mergers? So
we're not saying that all supermassive black hole masses are the same. What we're saying is the correlation between the mass of the supermassive black holes and the mass of stars in the galaxy is the same. So if the mass of stars in the galaxy is bigger, then the corresponding supermassive black hole mass will also be bigger. And we've got this straight line correlation between SMBHs and stars. So and what we're saying is that that's the same. That correlation is the same for our local galaxies, our intermediate galaxies, and our distant galaxies. So those lines, effectively, the ratio of those numbers should be the same for each different sample of galaxies, and that's borne out by observations and simulations as well. More importantly, classical simulations.
From Max, are there other ways to detect and measure black holes in distant galaxies?
Yes, there are. I mean, we think we know there's black holes because if you look in X-rays, we see the centers of galaxies having very strong X-ray emission as stuff falls onto black holes. It's heated to extreme temperatures, and you get this very hot accretion disk around the black holes that are observed at X-ray wavelengths. In the radio, we also see gigantic jets coming out of the centers of galaxy. Again, that's caused by matter falling off and being ejected from the centers of galaxies, and the only things that can do that are really black holes. So there are lots of ways to detect and measure black holes in distant galaxies.
Okay, question from Keith. So is dark energy an explanation for the inflation?
So I'll come back to that. But something like dark energy probably was responsible for inflation.
Okay, thank you. Oh, thanks, Chris.
Okay, let's move on. So let's move on to part 4. Okay, so we've had now what we've established so far. We've established that dark energy exists. We've seen it, but we don't know what it is. We know it's there. We've established that black holes have been observed. They exist. They're not theoretical objects. We've also established that what looks like a little bit of a conundrum here is that black holes are growing faster than what we predict by purely astrophysical processes. So how can black holes grow if they're not growing by accreting matter or swallowing stars or merging with other black holes? So here is it's general relativity here to the rescue. Yeah, what could possibly go wrong with this? I don't know. So general relativity has inside its mechanism. There's the possibility that black holes can actually increase their mass as the universe expands. So this is not, this is not work of a few years ago. This has been going on for the best part of 2 decades now. So there are solutions of Einstein's equations that predict that that mass will evolve with time as the universe expands. And in fact, mass growth is expected for relativistic material, regardless of where they are in space. So when we say relativistic material, we're looking at objects where gravity is very, very strong. So again, when we say relativistic material, it basically means black holes here. Okay, so there's general relativity makes a prediction that mass growth of relativistic objects in the universe can be linked to the size of the universe as it expands. So what we have here, in fact, when we put these, when we do the maths in general relativity, we find that we can have a black hole solution without singularities, so there's no crushing center of these black holes, without event horizons, so there's no point of no return, with certain cosmological boundary conditions which are not really explored properly for the classical models of black holes that we have today, and also a mass that increases as the universe itself expands. One of the key points here is that there are very, very good models of black holes in general relativity. There's the Schwarzschild model that we often study, in university. That assumes a static black hole, not rotating black hole, and that's how basically it's very easy. You can do you can look at energy considerations. You can use A level maths to do this. You can show the size of a black hole for a given mass for escape velocity of the speed light. It's like a 10-second derivation. There's also Kerr black holes. Now, a Kerr black hole is a rotating black hole, so a bit much more realistic. And again, these are really, really good models for black holes that we see in the universe. However, the key point here is that the Kerr model is basically based on short scales in space and time. Okay, so we're looking at black holes in an instant. We're not thinking about black holes as an evolving body over billions of years. So that's one of the key points here. So what we're saying is that black holes, being relativistic, their mass will increase as the universe expands. So they're intrinsically linked to the expansion of space and time. So you can imagine, again, we're using the rubber sheet analogy here with this with these three pictures. So we've got a black hole sitting on the fabric of space and time. Fabric of space and time is expanding itself, and as it expands, the mass of the black hole is increasing. And we say this is coupled to the expansion of the universe. And we're saying it's coupled in such a way that the mass of the black hole that you observe is equal to some initial mass in the past, and times the ratio of the size of the universe when it was observed compared to when it started, to some power. And this power here, this K, is called the coupling constant. And this coupling constant could be any number. So if you put K equals 0 in here, what we get is that the black hole mass you observe is exactly the same as the initial black hole mass. So that's sort of like what we have for a classical black hole if K equals 0. These are the black holes that we think we had in the universe until this recent study. So we can try and measure this value of K by looking at the evolution of the mass of black holes over cosmic time, using our elliptical galaxy sample that minimizes the effects of star formation, and see what comes out in terms of the coupling strength here. Okay, so when we do this, we assume we're going to fit this model to the data, and we should get the same value of K for every possible comparison across every redshift distance. So if we compare our green with our orange, we should get the same value of K as if we compare green with blue or orange with blue, if this is a universal relationship, which it needs to be if the mass growth is linked to the expansion of the universe. Okay, because the universe, doesn't undulate really as it expands up and down, and it doesn't get smaller and bigger, right? So it's this uniform expansion of the universe. Even if it's accelerating, it's the same. So what do we find? What do we find when we do this? So again, if we add this into the mix now, into our measurement of black hole masses, and we try and fit the best value of K to our mass evolution, what we find for our black holes is this is the distribution of, or rather the probability of the black hole mass here against the value of the coupling strength, K. And what we see is for all samples, right? All samples, or whatever sample you compare with each other, we basically get a peak at K equals 3. Right? Now, that in itself is quite exciting, but more than that, we see that this probability curve, it's nowhere near 0. It's nowhere near K equals 0. Now, K equals 0 is the value that we expect for classical black holes. So immediately, we're saying something very fundamental in that there's something else going on, and that our classical model of black holes might not be giving us the entire picture of how black holes evolve in the universe. Okay, so we can see that in fact K equals 0 is ruled out at the 99.8% confidence level. That's almost 4 sigma. So I know it's not a 5 sigma result. It's very 5 sigma result is very trendy in the news, but it's still a result. Yeah. Okay, so we also find that the best fit is K equals 3.11, so consistent, and there's a lot of scatter, admittedly, but it's consistent with K equals 3. So why is K equal 3 special? Okay, so let's think about K equals 3. So we know from this result, we know that the black hole mass increases as the cube, K equals 3, of the size of the universe. So the black hole mass is increasing as a cube of the universe expansion. However, as the universe expands, the volume of the universe is getting bigger. Therefore, the number density, the number of galaxies, the number of black holes per volume must be decreasing because the universe is stretching out. And so, the number of black holes in a 10 light year box billions of years ago, as the universe expands, goes down because that 10 light year box is now expanded to be 100 light year box with the same number of black holes in it. So that goes down as 1 over r to the cube. So putting these together, we actually find that the total mass energy density, so multiplying the m and the n together, will cancel out. So in fact, we find a constant for the total mass energy density of the universe. So now that should ring, that should ring some alarm bells here, right? A constant energy density as the universe evolves, right? So we know what that sounds like, right? We know that sounds like a cosmological constant or dark energy, right? So what's happening here? This is a nice little graphic from PBS actually here. So constant mass density is the hallmark of dark energy. And we can see the black hole mass is increasing. We can see the number density decreasing rather, but that bottom bar stays the same. Okay, so that doesn't move in the history of the universe. So we've got something in black holes with a constant energy density. And we get this, across whatever sample we look at. So this is saying, hey, black holes are acting like they contain dark energy. And you think, right, wow, this is new, but how can if you just pulled this out of thin air? And the answer is, no, not really, because in fact, there's actually an entire zoo of black hole types. So we've got the Schwarzschild and the Kerr, which is basically, what you would do at university, for example. Yep, your classical bare bones black holes. Then you've got Glinger, who we mentioned earlier. He actually predicted or postulated dark energy inside black holes many, many decades ago. We have other ones, for example, all these different papers that are published down here. They've all, for example, putting forward possible models where black holes contain vacuum energy or dark energy. Some are horizon free; they haven't got singularities at the center. You've got ones that grow in mass. So it's not a new result in terms of like black holes possibly containing vacuum energy in their interiors. So what does this mean? Right now we can go back to our initial picture of the universe. Now, can black holes, this mass growth in black holes, and under the assumption that black holes are actually containing dark energy because of this K value that fits it, can the black holes actually account for the dark energy in the universe? So even if we say black holes contain dark energy, do they contain enough dark energy to actually make up this 68%? And we can have a go at this. Because we know that black holes are only created by the deaths of massive stars. Created, not growing, remember here, created. Okay, so can the production and the growth of black holes give the observed value of the dark energy? So we can basically add up the star formation in the universe and relate that to the creation of big black holes and see what we get in terms of the contribution of the black hole dark energy to this total dark energy that we expect to see in the universe. Okay, so it's 68%, it's 0.68. Okay, so we can do this exercise and we can show this plot, which is basically here. This is the star formation rate here, and again, what you've got inside this this green envelope marks out the space where black holes could possibly contribute all the dark energy of the universe. And again, you've got various model curves here for star formation. So you've got the dotted blue, the green, the orange. All of these lines for star formation lie within the allowed range of black holes contributing the total amount of dark energy. So there's some points up here that don't agree. That again, okay, so these things need to be addressed and explained, but especially when you get to the distant universe in here, all the models and all the observations, in fact, the points, all lie within this admittedly large envelope where black holes can contribute the amount of dark energy required for the universe. So in fact, so we can say here that it's possible that dark energy in black hole can be enough to actually, explain all the dark energy away in the universe. Okay, so I think that's going to bring me to a summary here. So trying to summarize this enormously wide-ranging subject. So we look at supermassive black holes inside elliptical galaxies across 7 billion years of cosmic history. We find there's an 8 to 20 times preferential black hole growth compared to stellar mass growth relative to stellar mass. So we see this big difference in black hole growth. If we assume it's cosmologically coupled to the expansion of the universe, we see that we favor a K=3 solution, but we also rule out traditional black holes at a very high probability. So this is the first observational evidence for a black hole solution beyond the classical black hole solution, right? And it provides very interesting prospects for no singularities and no event horizons within black holes as well. The observational evidence it provides can ease the tension on black hole masses, for example, what we see in LIGO and what we see in high redshift quasars and other areas. It's also the first observational evidence for an astrophysical source for dark energy, right, from something we already know exists, so black holes. So again, I think this is one of the key point here, right? It gives us something that we can investigate, look at, and fine to disprove, but it's disprovable instead of just saying dark energy is there. It also solves the dark energy coincidence problem, which was an earlier question. Why does dark energy kick in 4 billion years ago in the past? It kicks in when the black hole mass density exceeds the other contribution from the dark matter and the normal matter in the universe. Okay, so lots of things to do. You've got to thoroughly vet the result, look at the various uncertainties, biases, ways to check it. We can look at the cosmic microwave background, see if we can find signatures there. We can look at orbital parameters of black hole merging. We have to check, does the coupling create two massive black holes at the local redshift 0? Look at cosmological simulations. We can look at lensing fractions of gamma ray bursts. And we can also look, which is very interesting, again, consistency with the James Webb star formation rate density. And I'll finish there.
Okay, brilliant. So thank you, Chris. We do have couple of questions that have appeared in the chat. We've got maybe about 5 minutes for questions. We like to wrap up not too long after 5 o'clock, so we do that. Just an observation from myself that what was fascinating to me is to, like, didn't seem that long ago to me that black holes seemed very theoretical. And now it's kind of becoming practical. The observational side really impressive, and how that's improved just over the last few years.
Yeah, I think it's brilliant, because I think we've had over decades, right? Since the 60s, black holes have been in the realm of theoretical discussions, and I think now, with the imaging of black holes, and also with testable theories, we're in quite a sort of like coming into a golden age of black hole astrophysics, I think.
Oh, yeah. So great time for you to be involved. So well done.
Yeah.
Yeah. So we've got about 5 questions. Let's see if we can at least do a few of them. So the first one from Colin: how can you have a black hole without an event horizon? As surely it would not be black. Yes.
So again, this starts to get into the different solutions you get from general relativity. Right? There are black hole solutions where the event horizon is not quite. I mean, it's very close to being a classical event horizon, but it's just above that limit. So the gravity is very, very strong, right? But it doesn't quite reach that classical limit. And in fact, when you couple this with the dark energy cores of black holes, you can actually get an interaction of basically 2 horizons: the interaction of the classical event horizon with the expanding horizon due to dark energy in the cores of black holes. Now, when these 2 horizons interact, it's almost like you get like this elastic sheet across the surface of the black hole, where light can be trapped or even absorbed into the black hole via some interaction with dark energy, which would actually increase the energy and mass of the black hole. But in theory, you could have a light particle that entered this black hole and would be able to escape past that classical limit of the event horizon. So again, like there's plenty of theories, which actually surprised me when I started looking at this. There's plenty of theories of black holes without horizons.
Okay, thank you for that. So from Heather: if supermassive black holes swallow up vacuum energy from the space around them, would not the whole density of the universe be lumpy?
Well, the density of the universe is lumpy, because we live on stars and galaxies and planets. Every time astronomers do like cosmological calculations and simulations, we often assume a uniformly distributed universe, right? And in fact, when we talk about normal matter and dark matter in the universe, and we say about them slowing down the expansion of the universe, we're still assuming they're uniformly distributed, but they're not, right? We know they're not. But we can assume that when we're talking about the whole mechanism of the universe. So if we can do it for normal matter, there's absolutely no reason why the same thing couldn't be done for dark matter, dark energy as well. Just because black holes are clumpy, the actual total effect is smoothed out over the entire universe, right?
Okay, I'm going to select a couple of questions here. So and it's great to see that everybody's. Well, firstly, we had 60 plus people attend, which was amazing. And it's great to see we still have a good set of people with us. So just to select a couple of questions. So from Keith: is there any proposed mechanism for converting dark energy into mass and vice versa?
Yes. Yes. It's not really enough time to go into it in detail, but yes, there is. We had this question about inflation at the start of the universe, right? Now, before inflation started, the universe didn't contain any matter that we understand as matter. Didn't contain the protons and neutrons and electrons. Now, inflation can be thought of very similar in a way to a phase change. For example, when water changes from ice into water or water into steam. Okay, so we can think of this, we can think of the inflationary universe, for example, being water in its ice phase. Right now, there's a phase transition as water goes from ice to liquid. Now, when that happens, there's an associated energy release, right? As the energy in the ice gets, energy locked up in ice gets released into the liquid. And we can see it even more when the water turns into steam, right? We can see that energy release when the water turns into steam. That energy release at the end of inflation is what is basically the Big Bang. Right? That's basically what the Big Bang is. It's when the Big Bang happens. So the Big Bang classically doesn't really happen at the beginning, right? It happens after inflation, right? And that energy creates everything we see in the universe. So that's changing a vacuum energy into matter, right? And that's a pretty good theory of inflation. So what we're talking about here, mass into dark energy, is basically running that inflation process backwards in time, right? So it'd be a very similar, it could be a very similar mechanism to that. There are theories that say like you get a gravitational condensate, very similar to what we see, like a Bose condensate at low temperatures and in particles. So there are lots of theories out there. I'm not qualified enough to go into like the minute details of those, but there are mechanisms out there. Whether it's provable, probably not at the moment. Okay.
I think we're getting close to time. So David Southwood, if you could emerge from the darkness.
Okay, I have done so. Thank you very much, Bill and Chris. What a performance. A lot of it even made sense to me. I was really delighted having, and I thought you chose a really challenging topic, bringing together black holes, dark energy, and galaxy evolution. I mean, it was, I think, a masterclass in how to present these things, and I really applaud. And as I say, you've almost convinced me. And it was a great performance, and I think it's really been a great way for all of us to start our weekend, and you, no doubt, to finish your working week. So I'd like to thank you very much, and perhaps we can turn on unmute everybody so we can show our appreciation in the usual manner. So thank you, Chris.
Thank you.